Question number 9 is rather lengthy, but this is kind of typical of paper 2 questions from IB. And in this video, I'm going to cover questions 9 through 13 from the end of chapter 5 on page 193 to 195. So the first thing they ask you to do is use this equation for the combustion of methanol, and then use bond enthalpy values from table 11 to go ahead and calculate the heat of combustion using bond enthalpies. So first thing you have to know is what bonds are in there. So if you draw this, you've got carbon with 3 hydrogens on it, an oxygen, and then another hydrogen. So that would be 3 CH bonds plus a CO bond plus an OH bond. And then the O2 is always double bonded to itself, so plus 1.5 times the value of an OH double bond. And then we're going to subtract the bonds in the products. CO2 is 2 CO double bonds. And H2O, each water has 2 OH bonds, so that's a total of 4 OH bonds. And the only thing I can cancel here is 1 OH bond can cancel from the left to the right. Otherwise, I just have to find my numbers and plug them in. So I've got 3 times 414 plus the CO bond is 358 plus 1.5 times 498 for the OH double bond minus 2 times 804 for the CO double bond plus 3 times 463 for the OH bond. And if I did my math correctly, I'm coming up with a delta H of negative 650 kilojoules per mole. In part B, then, they want you to look at the experimental data they've given you. And first they want you to calculate the amount in moles of methanol burned. So they've given you the initial mass and the final mass of the burner in methanol. So I just go ahead and subtract those, and I get 0.523 grams of methanol. But they actually want it in moles, so now I have to divide that by the molar mass, which is 32.05 grams per mole. And so my moles of methanol is 0.00163, I think it is. Just 0.0163 moles of methanol. In part B, we're asked to find the heat absorbed by the water. So I don't need this in kilojoules per mole. This is just going to be in joules because I'm going to use MCAT, the 20.00 grams of water, my specific heat value of 4.18, and my temperature change of 4.9. And rounded to just 2 sig figs, because I'm limited by my temp there, I come up with 410 joules, or 0.41 kilojoules. And this is positive because we're talking about the water absorbing this energy. But on part 3, then, when they ask you to calculate it as the combustion in kilojoules per mole, I use the 0.41, and now I'm talking about the methanol fuel. So now this is a heat loss, or negative 0.41 kilojoules, divided by the 0.0163 moles. And we're talking negative 25 kilojoules per mole. Part C wants you to compare the literature value for the combustion of methanol, which is over 700, to the 2 values we got. So one at negative 650 compared to the, I think it's 726, that's reasonable, and that can be accounted for because of the fact we used average bond enthalpies. And average bond enthalpies are averaged from a variety of compounds that have that same bond, not this specific compound that we're breaking the bonds in. So the fact we're using averages would account for that difference. In part 2, we have very little we have very little enthalpy there. Negative 25 is nowhere close to the minus 726 expected. So we've got some pretty significant air going on. Heat loss would be a big one. Incomplete combustion would be another possible one. And then the other one is when you look at the heat of combustion value that they got the minus 726 for, that's assuming methanol was a gas, and our methanol was actually liquid, not gas when we burned it. So that's also going to affect the values we get. Part C then wants you to look at, Number 10 is talking about a calorimeter experiment where you're finding the heat of a reaction, like in a coffee cup, similar to what we did in class. And they want to know what assumptions you're making. You're assuming density of the solution is equal to the density of your water, because that's how you determine the mass from volume. You're also assuming the C value of your solution is equal to the C value of your water. It's assuming you have a complete reaction going on in there, that your limiting reactant completely reacts, and that you have no heat loss to the cup or any of the surroundings. In part B1, you're asked to go ahead and calculate what the maximum temperature would be based on the line they extrapolated, and they give you the equation for the line there that T, capital T, or your temp, is equal to negative 0.050, that's your slope, and it's pretty insignificant, times little t, your time, plus 78. So if we take a look at this, this is what a lot of you did in our Hess's Law Lab. We can plug in 100 seconds for where we added the zinc into the HCl solution. So negative 0.05 times 100 seconds plus 78 gives us a T value of 73, which is our predicted maximum temperature, which is quite a bit higher, about 10 degrees higher than the actual recorded temperature. But it does make some assumptions. So it assumes that the heating of the solution was uniform throughout the cup, that our thermometer wasn't at a hot spot or a cool spot. And it also assumes that the cooling or the heat loss is constant. And according to our graph, that looks pretty constant. Our slope looks pretty uniform as we look across there. Part 3 then wants you to go ahead and calculate the energy gained by the water. So again, this will be a positive value since we're talking about it from water's perspective. So I had 50 centimeters cubed of water, or 50 grams I'm going to go with, times the C value of 4.18, and then using 73 as my maximum temperature, I have a delta T of 48.2. So that gives me 10,100 joules absorbed by the water, or 10.1 kilojoules. Part C, they mentioned that the color changes from blue to clear, and what that's supposed to indicate is that all the Cu2 ions were consumed, or Cu is your limiting reactant. Your other hint was that they didn't give you a mass for zinc. So in part C, to come up with the amount of moles in zinc which reacted, I have to look at how much limiting reactant I had. So I had 1 molar CuSO4, and I had 50 cc's, or 0.05 liters. So that means I had 0.05 moles of Cu2 plus. When you look at your equation, you see that the balanced equation shows 1 mole of zinc reacts with 1 mole of copper ions, so it's just a 1-to-1 ratio. So I also have 0.050 moles of zinc being used. And I know I dropped some sig figs there, but that's okay. And then part D, they want you to go ahead and calculate the heat in kilojoules per mole. So I've got my 10.1 kilojoules, my 0.0500 moles, which means using 3 sig figs, I have negative 202 kilojoules per mole of heat combustion. And it needs to be a negative because now we're talking about the heat lost during the reaction. Number 11, you have 2 students calculating the enthalpy change for this equation. It's called the hydrogenation because hydrogen's added and breaks a double bond and then saturates or fills up this hydrocarbon. And one uses the enthalpy values and does it theoretically, and the other one uses energy cycle using Hess's law. So 2 of the methods we learned in this chapter, and we're going to compare the values we get. So in A, it says calculate the enthalpy using the average bond enthalpies given in your data table. So first of all, I have to realize that C2H4 is going to be a double bond between the carbons. Hydrogen's going to have a single bond. And then because that double bond gets broken, my product is going to have just a single bond between the carbons and the 6 CH bonds. So if I look at this, on my reactant side, I have 4 CH single bonds, plus a carbon-carbon double bond, plus a hydrogen single bond. And on the reactant side, I have 6 carbon-hydrogen single bonds and a carbon-carbon. So I'm going to go ahead and reduce this to just 2 carbon-hydrogen bonds on the product side. That's the net difference. So when I plug in my values here, I can plug in 614 for the carbon-carbon double bond, 436 for my hydrogen bond, and then subtract my product 2 times 414 for the carbon-hydrogen, and 346 for the carbon-carbon single bond. And my net enthalpy change then is negative 124 kilojoules per mole. In part B, I've got Merritt's way of doing it, where she used these energy diagrams, and although this diagram looks very confusing, the idea is that my most direct path would be this equation right up here, but I don't have a value for that. But I can get a value by going down, down, so I end up here and here, and then I can go up. And when I do that, as I come down, the negative 1411 is the direction it was going. The negative 286 was the direction it was going. But I have to flip the 1560 to a positive 1560 because I'm going to reverse the direction. So using this energy diagram, I come up with a delta H of negative 137 kilojoules per mole, which is a little lower than the negative 202 I had in part A. So part C wants to know, suggest one reason why John's answer is slightly less accurate. Even though it's the higher value, it's less accurate than the known value, and that's because Merritt's values come from these exact bonds being measured experimentally. So Merritt's values equaled these bonds, whereas John's values are using average bond enthalpies. So his is going to be the less accurate. So then in part D, D1, use the average bond enthalpies to deduce a value for the enthalpy of hydrogenation. Of this time, it's something called cyclohexene becoming cyclohexane. And cyclo is just what it sounds like. It's a circle. So I've got carbon to carbon to carbon to carbon to carbon to carbon. So it's really a hexagon. And there's 10 hydrogen. So if I have 6, I can't put 2 on each hydrogen, which would fill it up. So I'm going to need 1 double bond in here, because that means these 2 carbons each only get 1 hydrogen. The others each get 2 hydrogens, and I'm just going to show the bonds so this doesn't get too crowded. So what that means is I've got 10 CH bonds in there. I have 1, 2, 3, 4, 5 carbon-carbon single bonds, and I have 1 carbon-carbon double bond, and then the H2. On the other side then, C6H12, that double bond's been broken, so now I have C 6 times around in my hexagon again, but now I have all single bonds, which means each carbon has 2 hydrogen. So now I've got 6 CC bonds plus 12 CH bonds. So I could do some reducing here and look at just 2 CH bonds and just 1 CC bond. And when I plug in the numbers here between the 2 sides, I've got the carbon-carbon double bond is 614, the hydrogen bond is 436, minus 2 times the 414 for the net carbon-carbon bonds, and the 346, I'm sorry, 2 times 414 for the net carbon-hydrogen, and then just the one carbon-carbon at 346. And that gives me a value of negative 124 kilojoules per mole. And in part 2, they say that the percentage difference between these is actually greater than it was for ethene up above when John did it. And John thought it would be the same, that the percent air should remain consistent. But their air actually increased because in this case, both the reactant and product are liquids, not gases. So we haven't taken into account the energy that would be needed to vaporize these two and give us a more accurate picture. Number 12 is a pretty straightforward bond enthalpy question. So N2H4, I'm going to just connect the ends with a single bond, put the hydrogens on, and see what I'm left with. And what you have to remember is that hydrogen has 5 electrons each for a total of 10, and then I've got 14 with the hydrogen. So I've used 2, 4, 6, 8, 10 bonds. Nitrogen each needs another pair, but they don't need to double bond to get that. They can just each take a lone pair, which is pretty common for period 5 elements. O2 is going to have its double bond. N2 actually needs to form a triple bond with itself and then has the 2 lone pair. And an H2O we're familiar with, that's going to be 4 OH bonds since there's 2 of them. So with nothing to cancel between my reactant and product side, I'm just going to go ahead and plug in 4 times 391 for my NH bonds, plus my NN bond is going to be 158. My oxygen double bond is going to be 498. Minus my reactants, I have a triple bond at 945, and I have 4 OH bonds at 463. So delta H calculated from bond enthalpies will be negative 577 kilojoules per mole. Number 13, this is similar to the questions they asked at the end of section 5.3 when they're talking about ozone and oxygen. We'll get into this a lot more later when we get into the organic chapter. But O3, what you have to remember is in order for O3 to form, it needs 1 single and 1 double bond, which means there's resonance, which means each of these bonds is really more like a 1.5 bond rather than a single and a double bond. Whereas with O2, it's just 1 double bond between them, which is a true double bond. So number 1 says, state and explain by reference to the bonding which the reaction requires a shorter wavelength. Well, smaller wavelength means higher frequency or greater energy. So which one has the stronger bond? And that would be 2. The O2 has a stronger bond because it's a true double bond, as opposed to O3, which is a resonant double bond, or really a 1.5 bond.